Thank you very much. I joined Frederick, and I hope you had a great lunch and you are caffeinated enough. So if anybody is dozing off, I'm not responsible. Today I will talk about pushing RabbitMQ to the limit. My name is Gabor Olah. I work for Erlang Solutions. We run Erlang and RabbitMQ consultancy. So my job is to basically talk to people and make sure that their RabbitMQs are up and running, healthy, and their design is correct to their needs. But today, I'd like to show you how you can feel where your RabbitMQs end, how far you can push them, and we try to do that without looking into the code. In the keynote, we heard about how the Erlang VM works. Hopefully you learned something useful. That is the one that powers RabbitMQ and gives it great scalability. We will see how that looks like with numbers. We also learned about some internals about the databases that run RabbitMQ and how they will evolve over time. It can't happen soon enough, so hopefully that plan will come through. But there is a way to see what Rabbits can do and what it cannot do. So as a consultant, I very, very frequently ask the question, shall we upgrade the CPU or add more memory? Usually this is from people who run into some kind of performance problem. Or what kind of disk should I use? By the way, the answer is SSDs and as quick as possible and as low latency as possible. Or is this particular topology good enough? And the answer is it depends. If it works, then probably. If it doesn't, then there's something to change there. Obviously, the answers are not so simple, and there are some better ways to phrase this. Now, what we really want is something like that. At least I would be happy with something like that. As complicated as it looks, it would be a nice formula. I plug in all the details of your system, and then at the end, it tells me that your system can do 72,000 messages per second. And you are either happy with that answer or not, but at least it would be something explicit. Unfortunately, that is not possible. So there is no easy answer, unfortunately, for this question. Why? Because computers are complicated. So RabbitMQ runs on the Erlang VM. That's one abstraction level. And we had a question at the end of the keynote that can you somehow map queue performance to CPU requirements? And if you think about it, Erlang runs these processes on some thread fairly that interacts with other processes. On a regular system that you start up and has a single queue, you have about 450 processes. If you add, let's say, 10,000 queues and 10,000 connections, and another 10,000 for consuming, because you separate your connections for publishing and consuming, because you do the right thing, then you are at least 30,000 processes. You have way more than that. Now, that complexity needs to be mapped down to 16, 24 cores, and that's not easy. Especially that you have other factors like disk, you have memory, what kind of architecture you run on. Do you run in a shared environment, for example? Probably if you run in the cloud, yes, you do. They claim that it does not affect anything, but yes, it does to a certain degree. Do you run on a hosted file system or a file system service, for example? For example, if you are on AWS, then yes, you do. They give you some SLAs and some guarantees, but it's not always a hard line. If you run your own servers, then you can control a lot of variables, but it's not so easy. What's easy, though, is calculating memory and disk. I give you a nice formula. Calculate how many messages you want to store in your RabbitMQs and for how long, and multiply it with your average message size, and that gives you a number that you double, and provision that much memory and disk at least. If it's too much, then talk to us and we can figure out how to optimize the system a bit better. But at the end of the day, if you want a safe RabbitMQ and you want to sleep well at night, then it's a good first approximation for that. network is usually the next question that I'm asked. The network is hardly ever a problem. I've never really seen a RabbitMQ that was not able to perform optimally because the network held it back. If you have high latency, though, on your network, then probably the network will limit your end-to-end latency, but it will be not RabbitMQ that suffer from that. Even if you mirror, network bandwidth is never really a problem. CPU and latency in general is the one that causes problems. So how can we tackle this problem? Usually what I do is try with something simple. So we go on a journey and try to feel for your system, or in this case, my test system that I built, and see whether it scales, how it scales, where do we hit a bottleneck, and if we hit a bottleneck, can we explain it? In this talk, I will give you hints what creates the bottleneck. I will not show you how to reach to that conclusion. If you want to learn more, join Mikhail's call later on today, who will talk about the internals of RabbitMQ and how to test and how to measure. If you don't get the answers there, then consult some of us, and we will help you out debugging your specific system. Now, why do I say your specific system? Because it will depend on how you run. I mentioned it again. I will give you numbers how to see that that is true. Now, once we get some baseline measurements, we try to tweak the simple system to something that looks more like a production system, and then we iterate a couple of times and see where it leads us. So let's see. Before we start, we will see a lot of throughput measurements. We will measure it by messages per second. Some of you use a different scale. You use messages per day. I created a nice mapping between the two. So think about which one you use, where you are on this scale, and when you see the numbers, then probably it will be easier to measure it to your system. If you feel that your system is performing way slower, or you've never seen Rabbit doing that many messages per second, then there is room for optimization somewhere there. If you have better numbers than what I show, then I'd like to hear about it as well, because I always like to see where Rabbit ends. So let's go with a simple setup. The simplest setup that I can think about is set up a RabbitMQ node, not clustered, create a queue, create an exchange, set up a publisher, a consumer, and push through as many messages as possible. To build a system like that, the Rabbit part is very easy. Building a performance test tool is not. So what I do is refer back to something that's already exists, well tested, and a really handy tool, which is called PerfTest. PerfTest can be downloaded freely. It is developed by the RabbitMQ team, and they do a great job making a tool that is able to push rabbits to the limit. It is a Java-based tool. It uses the Java AMQP client library. It uses AMQP 0.9.1. Probably it can 1.0, but that's a different protocol. And what we can do with it is tell the tool to set up one producer, one consumer, and then push as many messages as it can through that interface. So the limiting factor in this case will be RabbitMQ and what it can do. So I ran it on not mine, but a colleague's laptop. My laptop was upgraded. So I asked him to run this command with RabbitMQ 3.10.7 with Erlang 25.0.4. That was the latest that I could find 2 weeks ago when I created the slides. So this is the setup that I'm running. This Intel MacBook is about 3 years old, and we get numbers for the test setup that start around 111,000 messages per sec, then very quickly drops below 80,000-ish, and that's the baseline. This cooldown of throughput is suspicious. Something is going on behind the scenes, and if you test your Rabbit performance, let's say you are a developer and want to feel what's going on and don't want to buy big servers, then it's a good first approximation for a simple test. then you will find that inter-CPUs heat throttle your performance, so it drops down the frequency that it runs with, and eventually it slows down what you can do. It is not good because for a very short time you get really nice results, then you get really bad results, and if you try to run it a couple of times at different times of the day, then you will get completely different results. So you can't really trust these numbers. So what you can do is ask somebody with a better MacBook to run these numbers, and what you will get is a nice flat line, dips in the middle because probably I was waiting, while I was waiting for the test results, I watched some YouTube videos. So what we get is 175,000-ish average, and it's nice and flat. So if you run your production system with a single queue on a MacBook, this is a comparable result. And you watch YouTube videos as well. So the numbers alone don't really mean a lot of things. For example, the message size is 12 bytes. I think that's the default that PerfTest uses. Even if it is not 12, 10, or 14, doesn't really matter. It's very, very small. But what it shows is a couple of things. It shows that a single process on this system can push through at least, let's be generous, 200,000 messages per second. So the process performance, Erlang process performance, is not the bottleneck. And there is no real slowdown. The queue performance is not the bottleneck. It uses classic queues, not mirrored, completely safe. No disk. Disk is not involved in this case because we didn't have PerfTest to persist. We will see how that affects performance, by the way, later on. And it's nice and stable. We can run another kind of measurement, though, because probably you don't run a single queue. Probably you run multiple queues. So we can see how things scale. We can build another setup which has one producer, one exchange, 5 queues, 5 consumers to each of these queues. And when you publish a single message, it publishes it into a direct exchange with the same routing keys. So it will copy the message to every single queue, which is basically a fan-out. So if you want to test, for example, fan-out performance, then you can do that by running PerfTest, almost exactly the same as before, but with one producer and 5 consumers. Whenever you run a test like that, I highly recommend that you open the management UI, check out the exchanges and the bindings for that exchange, and see what is the kind of mess that PerfTest did for you. If you stop the PerfTest instance, it will delete all the queues. When you delete all the queues, it deletes all the bindings as well. So at least if you made a mess and you stop PerfTest, everything is gone. It deletes everything because the queues are declared as auto-delete. This will show a tiny problem when we move to Quorum queues, but there are solutions for that. So you ask your colleague to run the test for you because you already have the best laptop on planet Earth. And you will see that the heat throttle is even more pronounced in this case. The reason for that is because in the previous case, we had one queue, one channel for publishing, one channel for consuming, and these 3 processes were the heaviest part. And that laptop has 6 cores, so you had quite a lot of cores sitting mostly idle, and that didn't really produce a lot of heat. In this case, we run all the cores at 100% for probably a good 5 seconds, and then the heat throttling comes in, and then the performance drops. But what we can see is that we can still publish around 25,000 messages per second initially, and then it averages out around 18,000, and then multiply that by 5, that's the throughput on the other end. And this is another cautionary tale. I frequently end up with discussions where I ask our customers, what is your throughput that we need to aim for? And they tell me that we run 100 messages per second. And to be honest, 100 messages per second should be doable by a smartwatch in modern computing. And then we take a look at their management UI, and they are complaining about overload. and not enough throughput. And then we take a look at their management UI, and it shows that they are really publishing 100 messages per second, but they are consuming 10,000 because they do a massive fan out. So when you talk about throughput, think about both ends of this. So in this case, I'm doing on this machine around 150,000 messages per second combined. So think about these ideas. And then you run the same test on another machine, and it gives you a nice flat line. So it's stable. It doesn't necessarily slow down. It also shows that under normal circumstances, RabbitMQ behaves quite nicely with prolonged load. So it does not degrade over time. There are no internal bottlenecks. At least from this black box test, we could conclude that by running the test long enough, it didn't cause any performance degradation, which is nice. Now, unless you really run your production setup on your laptop, which probably you shouldn't, then let's move to something that is more production-like. For my test, I chose AWS EKS for a couple of reasons. One, that it burns my company's money, not mine, and I don't need to buy physical servers. It's easy to scale. I can set up multiple node groups with multiple instance types and turn one instance type down and or turn one node group down and just bring up another one, and I get a Rabbit cluster that's exactly the same, just on another set of nodes. And I can run different kind of tests. It's very flexible. And I highly recommend this. Even if you run your own data center, if you want to experiment with different machine types, because you've just seen that two different machines produce completely different results, and one outperforms the other, so you might as well upgrade your own servers to something more performant. But before you do that, try it somewhere else, and don't spend a lot of money on procurement if it doesn't help. So that was one reason. The other one is that I could use the topology operator for Kubernetes that is also developed by the RabbitMQ team, which is a really nice and handy tool because you define a need for a cluster, you tell it that you want 3 nodes, tell it to use pose minority in the config file, tell Kubernetes to make it happen, wait a couple of seconds, maybe a minute, and it happens. And you get a production-ready RabbitMQ cluster. So it's nice and handy. If you don't like Kubernetes, not everybody's cup of cake, I completely understand that. You can try it on try Cloud AMQP or Amazon MQ. They have a really good offering for Rabbit. If you run performance testing, you might as well talk to them and have their or ask for their advice. I'm pretty sure they are happy to help you out what is the best solution that exists. Or you can run bare instances in any cloud provider. I choose EC2, but you can go to Google Cloud as well, or Azure. It works the same way. Or you can run performance tests on your self-managed servers and obviously your production. So what we want is exactly the same setup now with the 3-node cluster because it's production ready. We want a publisher, a consumer, an exchange, and a queue, and publish this message through. So we run PerfTest again and establish a baseline. We need to change a couple of things here because it's quite painful to set up a VM and try to connect it to a Rabbit service. So what I do is push the PerfTest instance into a container, tell it to connect to the service that is grabbed from Kubernetes, find the default username and password in the Kubernetes secrets, because you no longer are able to use guest and guest. But if you have a special Rabbit somewhere, then you can use the exact same URI option to point to that Rabbit service. And tell it to use one producer and one consumer. PerfTest comes with really nice abbreviations, so you don't need to write down a lot of things. And when you start adding more and more options to PerfTest, it gets really handy that you can use 1 or 2 character abbreviations because your command line gets nice. If you want something more reproducible than command line, then the PerfTest tool had a hidden gem called PerfTest Multi. It's a Java class. You can specify a JSON file as your input options, and it gives you a JSON file in return with all the performance measurements that you can parse. So let's run this command and see what happens. Our sending rate is 55K in the first run, and the receiving rate is roughly half of that. Not great, so you stop it before it fills RabbitMQ, and run it again. Maybe next time you are luckier. And it seems that you are, because you are able to crash Rabbit even sooner if you just let it run, because you publish even more messages and receiving slightly bit more. So something odd is going on if you run this setup in this case. And to see what's going on, you open the UI. Probably you decrease the rate, and you need to be quick or provision big machines, because this is filling up your RabbitMQ by a good 50,000 messages per second at least. And even with 12 bytes, that's quite a lot. And I mentioned in the beginning that you should provision enough memory to handle all the messages that you push into RabbitMQ and keep in RabbitMQ. So what happens here is that if you check the UI, you can check where your consumers are and which node they are connected to. It turns out that the consumer is connected to a different node, and the messages are going into RabbitMQ on one node, published to the queue quite quickly, because it's just memory copy internally, and then they are consumed through another node, because RabbitMQ gives you location transparency. You just connect to a node in a RabbitMQ cluster, and you have access to all declared entities there without the need to know where they were declared. So it's quite nice, but performance-wise, there's a huge penalty, because now the messages are going from the queue to the RabbitMQ node to the consumer through the network, so they need to be serialized, not just memory copy. They are copied at least once, then sent through a TCP network, then copied in memory again, and then sent out to the consumer. And this gives us that huge difference in publish rate and consume rate. And we can try forcing a single node connection. And instead of connecting to a service address, we can tell Rabbit to connect to a single node in the cluster and rerun the tests. Then we get these results. So 50K versus 25K, give or take. Doesn't really make a big difference. This is still not great. So if you check out what's going on, you see that the exact same scenario is happening, but now it's symmetrical, which gives us something, repeatability. So it's great. We are not completely based on random, but still there's some randomness in the system. What we really want is this, not this. So the question is, if this is happening, and both messages are going through the TCP connection internally, then why do we not get a symmetrical result? And the answer is that publishing is cheaper than consuming, apparently. At least for some reason, RabbitMQ treats it cheaper. And you can feel it on a single node as well. This is the hardest part to explain, because it happens when you overload or push a good enough load on RabbitMQ with small enough load. Let's say if I would run something less than 25,000 messages per second, you wouldn't be able to see this difference, because both links would be able to handle the capacity. But for some reason, when you publish, you end up in this unlucky scenario that the scheduler kind of favors the execution flow of publishing over consuming, even though consuming is cheaper or should be cheaper. So something like that goes on in the background, and debugging it would require that you load Rabbit quite high. You try to measure what's going on, but you generate so much data that you skew the actual measurement, and you end up in this quantum computing situation that you observe the situation and it changes just because you look at it. So don't look. So we ended up with this setup. Not great, but it is what it is. We want that. We can enforce that. So what we can do is set up a policy, or probably two if you use both quorum and non-quorum. We can set the queue master locator. The second one is the important one for our test. Set it to client local. What it does is that the queue will be created on the exact same node where your channels are. And the channel will be where your producers are connected, or your consumers connected, depending on which one declares the actual queue. In terms of PerfTest, neither, because there will be a third connection that will create your queues and exchanges and bindings. But since we forced everything on the same node, this is exactly the same situation. And if you run that, we get a result that is better than what we got before, because on this instance, we got a good 18,000 messages, 118,000 messages. It tells us two things, that it works roughly the same performance as an Intel MacBook. Not too surprising, it runs an Intel chip. I'm running it on C5 4 extra large machines, restricting the individual ports to 12 cores. So we get Intel CPUs there. Those are sound CPUs, but it's good enough. It's compute optimized. And this is a good advice. RabbitMQ is computationally hungry. Erlang is not a number crunching machine, and RabbitMQ runs on Erlang, so it will be CPU hungry. Tricky because you push through data, so you would think that it's a data-intensive application, so you would benefit from a network-optimized or a memory-optimized machine. But it turns out that the best machine that you can run it on are compute-optimized ones. So if you set this policy, the next test run will force the queues where you want them to be. So we have a new baseline, 118,000 messages per second, roughly. What we can do now is to turn on publish confirm, because you shouldn't run any systems without publisher confirm, at least unless you have a really good excuse. But even then, your default should be publisher confirms. So we can turn on publisher confirm in PerfTest by specifying a option, -c or -- confirm, and tell it a window size. And let's talk about this window size. So when you publish a message into RabbitMQ, you can do it synchronously. You publish a message and wait for a confirmation from RabbitMQ that it received the message. If you don't use publisher confirm, you are publishing fire and forget. If something happens in RabbitMQ, then your message is lost. You didn't opt into the fail-safe. But there's a problem with this approach, that it justifies those who say on Google or on the internet that publisher confirm is slow, because you send the message and you wait a very long time. That's the left side rectangle. Then the message arrives into RabbitMQ. RabbitMQ very quickly publishes it, and then sends you back an acknowledgement, and you still wait a very long time for that acknowledgement to arrive. So basically what you are doing is waiting for this propagation delay to happen, and you are not publishing anything. So both systems are sitting mostly idle, and what you see is a very slow throughput. To fix that, what you can do is send more messages into RabbitMQ without waiting for confirmation, not infinitely many. At one point, you should say that this is enough exposure to any kind of message loss. So let's say at 100 or 50 or 200, you stop sending messages until you receive a confirmation, and then you send another message, and then you send another message when you receive another confirmation. So at least it gives you a much smaller time frame when you are sitting idle. And if you find an optimal value, you can get very high throughput rates, even with publisher confirm. Let's look at that. So hopefully those in the last row can also see it. But if you set the window size to 1, our nice baseline, which was around 108, maybe not 118, but 108,000 messages per second, dropped to below 4,000. So it's quite a big drop. And this is what a lot of people say, that we turned on publisher confirm, and it does not perform. And what they are saying is they have a very high latency network, which we have in AWS most of the time if you don't pay for it. And I didn't pay for it, to be honest. So you double the window size, you double the performance, or the throughput. You double the window size, you roughly double the throughput. You do it a couple of times, and you end up with a roughly optimal value, which is around 100 in this case. I didn't run very granular numbers because at the point you are fighting for diminishing returns. But what I did is kept increasing that number. And then what happens is that performance starts dropping. Why is it dropping? Because you send a lot of messages up front, and you micro-overload RabbitMQ for a very short time. So Rabbit overload protection kicks in and tells you, please don't send more messages for now. Then it processes its backlog, then unblocks you, and they send another lot of messages, and then rinse and repeat, and you end up with a less optimal value because you are sending too many messages. It also shows that if you use publisher confirm wisely, then you get overload protection for free. You should use it because you care about message safety, but you cannot really overload RabbitMQ, because as you overload RabbitMQ, Rabbit slows down, and it will send you the confirmation slower. So you send messages slower, and that gives Rabbit some time to recover, and eventually it reaches an equilibrium. So any kind of publisher confirm is better than no publisher confirm, and it is kind of a requirement. And it can perform given enough window size. Unfortunately, the window size part and turning on publisher confirm is not a Rabbit configuration option. It's a client-side configuration or client-side redesign, so it's better to put it from the get-go than trying to retrospectively modify your clients. Now we have something with a single queue that can perform with publisher confirm. So let's see how we can change the topology. Because unless you run with a single classic queue, no mirroring, no quorum, probably you run with more than one queues. But as we've seen before, if you just increase the number of producers with PerfTest, it will create you a fan-out topology. That's not necessarily great because what is a much more frequent use case is that you have services that communicate on this horizontal level. So producer 1 pushes to consumer 1, publisher 2 pushes to consumer 2, and you get one message to one queue. So one producer, one queue, one consumer, and that is 5 times. How to make that happen? With PerfTest, it is possible. What you need to do is set up a queue name pattern, which is the bottom line from, or the third line from the bottom. So you set up a queue name pattern where you can put an percentage D, which denotes a number or replaces a number that ranges from the queue pattern from 1 to the queue pattern from 2 parameters. So if you run this, you will end up with 5 queues. They will be called PerfTest dash 1, 2, 3, 4, 5. And each producer that you specify with the X5 will be publishing with a unique routing key that is uniquely bound to that specific queue. On the other end, if you have enough consumers to cover the queue patterns, then each queue will have a single single consumer. And then you can run this number of publishers, number of consumers. And I'm seeing that I'm running out of time, so let's speed it up. So if you run this test, number of queues with this one-to-one pattern, then you can see that with one queue, on this specific setup, we were able to push 75,000 with 2 queues, 110-ish, with 4 queues, almost reaching 150. And then with 8 queues, we reached over 150,000. And then, as we added more and more queues, remember we only have 12 cores on this node, which we are loading, the performance didn't really drop much, but the latency increased. So it performs quite well even during overload. Now, we haven't persisted anything yet, so let's turn on persistency. What we can do is specify the -f persistent parameter to PerfTest, run the same tests again, and see how persistency affects performance. And what we see is that it affects performance quite a lot because the disk latency is very, very high. I'm using GP2 storage class for this, so it's not the highest latency or lowest latency solution, and that shows. So queue performance drops. This is, again, still classic queues, but it increases quite linearly. And when you start overloading, it drops a bit, but not too much. So it works quite well. Let's move on to an even more robust solution, move to quorum queues. Persistent queues were quite good as a baseline, because at least we hit the disk in that case. Quorum queues always persist messages, no questions asked, which is really good, because that is a default that a lot of people want. So if we just swap everything to quorum queues, then we will get probably lower numbers, because instead of just pushing onto a single node, we replicate to 2 others as well after we push to quorum queues. So any kind of drop here is not so surprising, because we do more work. And this is generally true as well, that if you increase the quorum size, the performance will drop because you do more work. So let's see the numbers. With 1 queue, the red one is quorum, the blue one is the previous result with the persistency. With 1 queue, it matches roughly the same performance. With 2 queues, it's lagging behind a bit, but not too bad. With 4 queues, it increases. And with 8 queues, we roughly reached the maximum that we can do in this setup. Remember, we only had 12 cores. So if we saturate all 12, then eventually we can't do more. And this is what we see, that we get some incremental improvements with 16 and 32, but it's not too bad. And it doesn't really drop performance. And these numbers are actually quite high, because we are over 60,000 messages per second. And that easily takes you to around 10 billion messages per day. So that's not a small load for any setup. And as I promised, there is a message size comparison. You can set the message size by specifying the -size option. It is measured in bytes. And as you increase the message size, the throughput drops. And it drops quite okay-ish. So on the horizontal scale, we multiply the numbers by 10. So instead of 12, 10, that's roughly the same ballpark. The second one is 100. The third one is 1,000 byte. And this is what a lot of people use RabbitMQ, so in this below 1 kilobyte message size range. And the performance drops a bit, but considering that we increased the message size by 100 times, the performance didn't even drop twice or 2 times. So it's quite good. After that point, we hit a wall, though, and GP2 shows its nasty property that we hit a limit, and it throttles us back. And since we push more data than we provisioned, it brings the performance basically to 0-ish once you reach the 1 megabyte range. So quorum queues don't really like big messages in general. Performance can be better than that. That graph that you don't see is below 10 in comparison, the very last one. So Quorum Queues can do a bit better with 1 megabyte messages, but after that, I've never seen any system that was better than that. So it's a good rule of thumb, if you can, use small messages because it will improve your performance. Especially if you use JSON or XML through Rabbit, then just compress it, and it will be a much better and easier solution than anything that you try to apply, and you are not fighting the system. You have a lot of other options as well. You can define the exchange, so you can predefine your own topology if you want. You can specify routing keys. You can connect PerfTest to multiple RabbitMQs, and the connection recovery is implemented correctly. You can specify how long you want everything to go. You can change the rate, latency, and size parameters based on the time, how long the test ran. You can requeue things, and most importantly, read the help, because it gives you probably another 50 other options that you can tweak. So in conclusion, can RabbitMQs do a high throughput? It heavily depends on how you use it. And there are so many variables that you really need to test your own system. Thank you very much.
Thank you.